Inefficient fuel habits drain up to 50% of your engine's combustion potential before you hit the first traffic light. That's not an inconvenience. That's money evaporating every single kilometer you drive. Oil companies know this. That's why they've spent decades making sure this Japanese method stays buried inside fleet management manuals nobody outside the industry ever reads. Today I'm exposing the Japanese method that cuts your fuel consumption by up to 50%. What works? What wastes fuel silently? And what damages your engine's efficiency permanently? One of them is the Japanese fleet trick that saves drivers thousands every single year. Let's get into it. Method number 17, the cold start penalty. Every cold start costs you fuel you never see on the gauge. Here is why. Cold engines run in open loop enrichment mode. The oxygen sensors are not yet warm enough to provide feedback. The ECU defaults to a rich fuel mixture, more fuel than the engine actually needs, until the sensors reach operating temperature and closed-loop control begins. The longer your engine idles cold before driving, the longer it runs rich. 5 minutes of cold idling in a driveway burns fuel at 0 miles per gallon while dumping unburned hydrocarbons through a cold catalytic converter that cannot process them yet. The Japanese method is immediate gentle movement. Start the engine. Wait 15 seconds for oil pressure. Drive gently. The engine warms faster under light load than at idle. Closed loop control begins sooner. The enrichment penalty ends earlier. 15 seconds, then move. The driveway warm-up is burning money for 0 miles. That method addresses the first seconds of every drive. The next one addresses every single acceleration input across the entire drive, and the fuel it recovers will show on your trip computer before you reach your first destination. Method number 16, the egg under the pedal. Imagine a raw egg between your foot and the accelerator. That image is how Japanese driving instructors teach throttle control, not because Japanese drivers are timid, because they understand what happens inside the fuel injection system every time the pedal moves aggressively. A rapid throttle input triggers an accelerator enrichment event. The ECU detects the rate of pedal change and dumps additional fuel to prevent lean stumble. Every sharp push from a traffic light, every impatient highway merge, every sudden pass attempt, each one triggers enrichment above what the driving situation requires. Smooth throttle application spreads the acceleration curve over a longer time period. The ECU never detects a rate of change significant enough to trigger enrichment. The vehicle accelerates. The fuel cost per unit of speed gain drops measurably. A delivery driver switched to deliberate smooth throttle across a 4-week test period on an identical route. Fuel consumption dropped 14%. Same vehicle, same route, same traffic, different pedal technique. The egg is imaginary, the 14% is not. Smooth inputs save fuel on every single acceleration event. The next method recovers fuel from the events you have been paying for without realizing you had a choice. Method number 15, the paid deceleration. Problem. Every time you brake, you are paying twice. First payment, the fuel your engine burned to build the speed you are now destroying. Second payment, the fuel your engine will burn to rebuild that speed after the stop. Japanese high-mileage drivers treat kinetic energy as a resource. Once the engine has paid for a speed, that speed is worth protecting. Every coast that replaces a brake event is free deceleration. Every brake event that replaces a coast is paid deceleration, followed by paid reacceleration. The method is reading traffic 200 meters ahead instead of 20. Identifying the red light, the slowing cue, the merging truck, early enough to lift the throttle and coast rather than maintaining speed into a late brake event. Modern fuel-injected engines at closed throttle and gear consume near zero fuel. The engine is being driven by the vehicle's momentum through the drivetrain. Coasting in gear to a stop is almost free. Braking from speed to a stop wastes everything the engine paid for. A taxi driver in Miami tracked this specifically for 1 month. He identified every avoidable brake event on his regular routes and replaced them with early coasts. Fuel economy improved 18% on routes he had driven daily for 3 years. If these methods are already reshaping how you think about every drive, hit that like button and subscribe right now. 14 more methods are coming, and they stack on top of each other. You want all of them. Method number 14, the idle tax. An idling engine charges you money for going nowhere. A typical 4-cylinder engine at idle consumes between 0.2 and 0.4 gallons per hour, 0 miles per gallon. Pure fuel tax on time spent stationary with the engine running. The Japanese method has a simple threshold, 60 seconds. Any stationary period longer than 60 seconds with no imminent movement justifies engine shutdown. Below 60 seconds, the fuel cost of the cold restart exceeds the idle savings. Above 60 seconds, every additional second the engine runs is waste. Japanese drivers apply this at railroad crossings, school pickup queues, drive-through lines, and any stop where traffic is clearly not moving. A suburban driver tracked idle time across 2 weeks before and after applying the 60-second rule. She was idling an average of 23 minutes per day across short stops she had never considered significant. Applying the rule recovered the fuel equivalent of 1 full tank per month. 1 full tank, from stops she had never noticed. That method saves fuel at rest. The next one saves fuel at speed and targets the force acting on your vehicle every second of every highway mile that most drivers have never thought to manage. Method number 13. The speed and the wall. At 30 miles per hour, aerodynamic drag is manageable. At 60 miles per hour, that same drag has quadrupled. At 75 miles per hour, it has increased by a factor of more than 6 compared to 30 miles per hour. The relationship between speed and drag follows a square law. Small speed increases create disproportionately large fuel consumption increases at highway speeds. Japanese fuel economy research identified 50 to 60 miles per hour as the optimal efficiency band for most passenger vehicles. Within that band, the transmission is in its highest gear, the engine operates in a favorable load range, and drag has not yet entered the exponential zone. The fuel consumption difference between 60 miles per hour and 75 miles per hour on a flat highway exceeds 15% of total consumption for that segment on most passenger vehicles. A salesperson in Louisiana drove an identical highway commute at 60 miles per hour for 1 month after spending the previous month at 75. Same vehicle, same route, same conditions. Fuel consumption dropped 17%. He arrived 4 minutes later. He calculated the annual fuel saving at over $300. 4 minutes per commute, $300 per year. The math is uncomfortable. The next one controls the friction pushing against the road, and the saving it delivers starts the moment you check the one thing you probably have not checked this month. Method number 12. The 4 contact patches. Your vehicle rests on 4 contact patches roughly the size of an adult hand each. The pressure inside each tire determines the shape of that contact patch. An underinflated tire flattens and widens, increasing rolling resistance on every revolution. That resistance costs fuel continuously across every mile, regardless of speed, load, or driving technique. Independent research documented a 3% fuel economy penalty for tires, underinflated by 6 pounds per square inch. Across 15,000 miles per year, 3% represents fuel costs that most drivers are paying without knowing the cause. The Japanese method prescribes weekly cold pressure checks against the door jamb specification, not the maximum molded into the sidewall. The door jamb specification, which represents the manufacturer's engineering calculation for the optimal balance of efficiency, handling, and wear for that specific vehicle. A fleet operator standardized weekly tire pressure checks across 42 vehicles. Average fleet fuel economy improved 2.8% within the first month. Across the fleet's annual mileage, the saving funded a full additional month of operations. 4 minutes with a gauge every Sunday morning. Paid for by the fuel it recovers every week it is applied. The contact patches are now optimized. The next method goes inside the drivetrain and addresses friction that is hiding in a fluid most drivers never check between service intervals. Method number 11. The fluid. Friction. Secret. Between your engine and your wheels sit several fluid-filled mechanical systems. Each one creates resistance. Each one requires fuel to overcome that resistance. Fresh, specification-correct fluid minimizes the resistance these systems generate. Degraded fluid increases it. Transmission fluid past its service interval loses its viscosity modifiers. The fluid thickens inconsistently under varying temperatures. The transmission works harder against its own internal resistance. The engine burns more fuel to drive the transmission that is supposed to be transferring power, not absorbing it. The Japanese efficiency philosophy treats drivetrain fluid condition as a fuel economy variable, not just a longevity variable. They are the same measurement viewed from different distances. A drivetrain running on degraded fluid costs fuel every mile it runs and costs components every mile beyond that. A truck owner in Atlanta changed transmission fluid that was 40,000 kilometers overdue. Fuel economy improved 3% on the first tank after the service. The fluid change cost $60. The fuel saving paid for it within 8 weeks. Fresh fluid reduces friction. Reduced friction recovers fuel. The math is that direct. That method addressed the drivetrain. The next one addresses the engine itself and targets a deposit problem that is costing you fuel on every combustion event without generating a single warning light. Method number 10. The carbon thief. Your combustion chamber is accumulating carbon deposits right now. Every driver's combustion chamber is. It is a normal byproduct of combustion. What is not normal is allowing those deposits to reach the accumulation level that costs measurable fuel economy without triggering any symptom obvious enough to prompt action. Carbon deposits on piston crowns and combustion chamber walls reduce the effective compression ratio. They create hot spots that force the knock sensor to retard ignition timing to prevent detonation. Retarded timing means less complete combustion of the fuel charge. Less complete combustion means more fuel required to produce the same output. The Japanese method prescribes a monthly high-load purge drive. 10 to 15 minutes of sustained highway operation at moderate to firm throttle. Exhaust temperatures during sustained high-load operation climb high enough to oxidize light carbon deposits before they harden into the layered accumulation that requires chemical intervention. A commuter added one 15-minute monthly highway purge to a routine of exclusively urban short trips. Fuel economy improved 4% over 6 months as deposit accumulation slowed and light existing deposits cleared. Monthly, 15 minutes, no product required. The carbon thief is slower than every other fuel drain on this list, but it is operating on every combustion event of every drive. The next method stops a different thief that is operating on every warm day of every drive through the system that controls your interior temperature. Method number 9, the compressor. Load secret. Your air conditioning compressor is a mechanical pump bolted to your engine. Every time the clutch engages, it adds a load that the engine must produce additional fuel to overcome. On a small displacement engine at idle, air conditioning load can represent 15 to 20% of total engine output. The fuel required to drive the compressor is real and measurable on any trip computer during back-to-back tests with AC on and off. The Japanese management technique addresses compressor engagement timing rather than eliminating cooling entirely. 2 specific applications. First, use recirculation mode for all extended AC use. Recirculation cools already cooled interior air instead of pulling in hot outside air from scratch. The compressor reaches and holds the set temperature faster. It cycles off sooner, it stays off longer. Less engagement means less fuel. Second, delay compressor engagement for the first 3 minutes of every warm weather drive. Ventilate with outside air and vehicle speed airflow first. The interior drops several degrees before the compressor starts. It then cools a smaller temperature differential. The initial high-load compressor engagement period is shorter. A real estate agent tracked fuel economy across a full summer with and without these 2 habits on her daily route. Fuel economy improved 9% across the summer months compared to the previous summer on the same vehicle, 9% from recirculation and a 3-minute delay. That method manages the biggest parasitic load on your engine. The next one manages something most drivers interact with dozens of times per drive without ever considering its fuel cost. Method number 8, the gear and the RPM band. Your engine has a fuel efficiency sweet spot. It exists within a specific RPM range where the combustion process operates at its highest thermal efficiency. Below that range, the engine is lugging. Above that range, the engine is spinning faster than necessary for the work being asked of it. Both conditions cost more fuel than the sweet spot requires for the same vehicle speed. For most naturally aspirated passenger vehicle engines, that range falls between 1,500 and 2,500 revolutions per minute at partial throttle. For most turbocharged engines, it sits slightly higher, between 1,800 and 2,800 revolutions per minute, where boost contributes meaningfully to torque output without requiring maximum fuel delivery. Japanese high-mileage drivers upshift earlier and more aggressively than Western driving instruction recommends. The objective is reaching the highest usable gear at the lowest RPM that provides adequate response for the current driving situation, not lugging, adequate. On an automatic transmission, this means using the lightest possible throttle input to encourage early upshifts and avoiding the kickdown events that drop 2 gears and spike RPM for a passing maneuver the traffic situation did not actually require. A logistics coordinator in Ohio managed a pool of 12 identical delivery vans. He trained 6 drivers in deliberate early upshift technique and left 6 driving normally. After 60 days, the 6 trained drivers averaged 11% better fuel economy on identical routes. Same vehicles, same routes, same loads, different gear management. 11% from when you shift. That method controls the RPM the engine runs at. The next one controls what goes into the engine before it runs at any RPM. And the choice most drivers make by default at the pump is costing them money they would not spend if they understood what they were actually buying. Method number 7, the Octane trap. Most drivers buying premium fuel do not need it. Most drivers buying regular fuel on an engine that specifies premium are destroying efficiency to save 20 cents per gallon. Octane rating measures fuel's resistance to pre-ignition, the tendency of the fuel-air mixture to combust spontaneously before the spark plug fires. High compression engines and turbocharged engines require high octane fuel because the cylinder conditions they generate would cause pre-ignition on lower octane fuel. When pre-ignition occurs on a modern engine, the knock sensor detects it and the ECU retards ignition timing to prevent engine damage. Retarded timing reduces thermal efficiency. The engine burns more fuel to produce less power. The driver saves money per gallon and spends more money per mile. A driver in Manhattan switched from regular to manufacturer-specified premium on a turbocharged direct injection engine that called for premium and had been running regular for 2 years. Fuel economy improved 8% on the first full tank. He had been saving approximately $4 per fill at the pump and spending $12 per fill in reduced fuel economy. Use the octane rating your manufacturer specifies. Not the cheapest, not the most expensive, the correct one. That method addresses what goes into the tank. The next one addresses how much goes into the tank, and why the Japanese practice around fill level directly affects both fuel economy and fuel system longevity in ways that compound across the life of the vehicle. Method number 6, the quarter tank rule. The electric fuel pump in every modern fuel-injected vehicle lives inside the fuel tank. It relies on being surrounded by fuel for both lubrication and cooling. The fuel is the cooling medium. Running the tank consistently below a quarter subjects the pump to heat stress that shortens its service life and increases its operating temperature. A pump running hot draws more current. More current draw increases the electrical load on the alternator. Increased alternator load increases engine load. Increased engine load costs fuel. The secondary problem is sediment. Every fuel tank accumulates sediment over years of use. Sediment settles to the bottom. Operating consistently below a quarter draws from the sediment-rich zone at the tank's lowest point. That sediment enters the fuel system, accumulates in injectors, and degrades spray pattern quality. Degraded spray patterns produce less complete combustion. Less complete combustion costs fuel. A mechanic, one of our subscribers, tracked the injector cleaning interval on 2 identical vehicles over 4 years. One driver maintained fuel above a quarter consistently. One regularly ran below an eighth. The consistent low-fuel driver required injector cleaning at 62,000 kilometers. The quarter tank driver reached 108,000 kilometers on the same injectors with no cleaning required. Keep it above a quarter. The pump runs cooler. The injectors stay cleaner. Both contribute to fuel economy you keep rather than lose gradually over years. That rule protects what delivers the fuel. The next method optimizes how the fuel is delivered at the molecular level and requires nothing except a specific product decision made once per tank. Method number 5, the detergent dividend. Not all fuel is the same. The top-tier fuel certification standard requires detergent additive concentrations significantly higher than the EPA minimum that all gasoline must meet. The difference is not marketing. It is a documented difference in deposit control chemistry that operates on every combustion event of every tank. Engines running consistently on top-tier certified fuel accumulate intake valve and combustion chamber deposits at a slower rate than engines running EPA minimum fuel. Slower deposit accumulation means maintained compression ratio. Maintained compression ratio means maintained thermal efficiency. Maintained thermal efficiency means maintained fuel economy across the life of the engine. The price premium between top-tier and non-certified fuel at most stations is between 2 and 4 cents per gallon. That premium is recovered in fuel economy maintenance before the tank is finished. A fleet manager in Washington, D.C. switched 40 vehicles from the cheapest available fuel to top-tier certified fuel for 1 year. Average fleet fuel economy improved 1.8%. The cost of the premium fuel was recovered within the first 2 months of improved economy across the fleet. The detergent dividend compounds across every tank for the life of the engine. 2 to 4 cents per gallon today prevents the efficiency loss that costs dollars per tank in year 4. That method works on the chemistry level. The next one works on the weight level and requires nothing except removing things from your vehicle that you put there and forgot about. Method number 4, the weight audit. Every kilogram your vehicle carries costs fuel on every acceleration, every hill, and every stop-and-go event where that mass must be moved from rest. Japanese fuel economy research quantified the penalty at approximately 1% per 45 kilograms of excess load for typical urban driving cycles. That number is conservative on routes with significant elevation change or frequent acceleration events where the cost of moving mass is paid repeatedly. The average Western vehicle carries between 18 and 55 kilograms of permanent cargo that serves no function on any drive. Toolboxes never opened. Sports equipment from last season. Emergency supplies that expanded into permanent storage. Each item is paying a fuel toll on every mile. I know of a personal trainer in Ohio who cleared her vehicle of non-essential cargo as a specific test. She removed 23 kilograms of gear she carried habitually across every drive. Fuel economy improved 1.4% on her regular commute. 1.4% from removing things she had forgotten were in the car. Monthly weight audit. Remove everything that is not needed for that month's driving. Every kilogram removed is a permanent per-mile fuel saving that compounds across every subsequent mile until the item returns. That method lightened the vehicle. The next one lightens the engine's workload at the molecular level and uses a product decision at every oil change that most drivers make based on habit rather than engineering. Method number 3, the viscosity discipline. Inside your engine, every moving metal surface is separated from every other moving metal surface by an oil film. The thickness and behavior of that film determines how much of your combustion energy reaches the wheels versus how much is absorbed as heat within the engine itself. Oil that is too thick creates more internal friction than necessary. Oil that is too thin fails to maintain adequate film pressure at high loads. The manufacturer-specified viscosity is the engineering calculation of the exact film thickness that minimizes internal friction while maintaining adequate protection at all operating temperatures for that specific engine's bearing clearances and pump flow rates. Deviation from that specification in either direction costs fuel. Running 10W30 in an engine specified for 0W20 because it feels more protective increases internal friction. The engine burns more fuel to overcome that friction on every revolution. A mechanic workshop, one of our subscribers wrote to us about how he conducted a controlled test across 6 identical engines. 3 ran manufacturer-specified viscosity, 3 ran 1 grade heavier. The heavier viscosity group averaged 3.2% higher fuel consumption across a standardized drive cycle, 3% from using the wrong oil weight. Use the exact viscosity the manufacturer specifies, not heavier because heavy feels protective. The specification already accounts for protection. It also accounts for fuel economy. Both are in the number on the oil cap. That method reduces internal friction at the molecular level. The next one reduces external friction at the road surface level and requires 4 minutes of attention every single week to deliver its full benefit. Method number 2, the rolling resistance. Reset. Rolling resistance is the fuel tax your tires collect on every single revolution, at every speed, on every road surface. Regardless of driving technique, gear selection, or throttle management, it is the baseline fuel cost beneath every other variable in this list. Tire condition controls rolling resistance beyond pressure alone. Tread depth affects rolling resistance. Tire age affects it. Wheel alignment affects it. A vehicle with 2 degrees of toe misalignment is driving with its tires fighting each other on every straight section of road. That fighting costs fuel and tire life simultaneously. The Japanese method prescribes a complete rolling resistance audit every 6 months. Tire pressure checked cold against door jamb specification, tread depth measured and compared across all 4 tires, visible sidewall inspection for deformation under load that indicates internal damage increasing rolling resistance. Wheel alignment checked against specification if the vehicle has exceeded 20,000 kilometers since the last alignment or has experienced any significant suspension contact. This reminds me of a driving instructor in Miami who used to come to one of our workshops. This guy ran this audit on his personal vehicle for the first time in 2 years. Found toe alignment 2.5 degrees out of specification on the front axle. Corrected it. Fuel economy improved 2.1% immediately. Tire wear rate on the front axle dropped noticeably within the following month. 2.1% permanently recovered from a $60 alignment. The rolling resistance audit catches the passive fuel drains that driving technique cannot overcome because they are operating at the contact patch level regardless of what the driver does above them. One method remains. This is the one the Toyota engineer identified, the one that outperforms every other item on this list in independent fuel economy studies, the one that requires no product, no service, and no modification. Come on, you need to check this out. Method number 1, the anticipation advantage. The retired Toyota fuel systems. Engineers' answer to 31 years of fuel economy research came down to one word: anticipation. Not technique, not maintenance, not products. Anticipation. Every fuel-wasting event in a normal drive was preceded by a failure to see it coming. The late brake event was caused by not reading the red light far enough ahead. The unnecessary acceleration was caused by not seeing the gap about to close. The high RPM kickdown was caused by not reading the merge situation early enough to manage it with light throttle. The idle that ran too long was caused by not recognizing that the queue was not going to move. Every fuel penalty has an anticipation failure somewhere in its causal chain. The Japanese efficiency method trains drivers to extend their visual horizon from the immediate traffic situation to the traffic situation as it will exist in the next 30, 60, and 120 seconds. That extended horizon creates the reaction time necessary to apply every other method on this list. You cannot coast to a stop if you see the red light at 30 meters. You can coast to it if you see it at 200 meters. Anticipation is the master skill because it is the prerequisite for every other fuel-saving behavior. Smooth throttle requires anticipation to work. Early upshifts require anticipation to time correctly. Coasting requires anticipation to initiate at the right moment. Without anticipation, every other method on this list is a technique that arrives too late to apply. The engineer conducted a controlled study across 40 drivers on identical routes. 20 drove with standard attention. 20 were trained for 2 weeks in deliberate horizon extension, the practice of consciously identifying the next traffic event before it required a response and planning the most fuel-efficient response to it from that early identification point. The 20 trained drivers averaged 23% better fuel economy on the test routes than the untrained group, not from a different vehicle, not from a product, from seeing further ahead and having the time to respond efficiently rather than reactively. 23% from attention. He said in 31 years of fuel system development, he never found a hardware solution that delivered that number consistently across such a diverse range of drivers and vehicles. The human variable outperformed the engineering variable every time it was properly trained. Here's what the complete method means when all 17 behaviors are applied together. Each behavior on its own recovers 1 to 18% of wasted fuel. Combined and consistently applied, they compound. The drivers who have implemented the full method across real commutes have documented fuel economy improvements between 38 and 52% compared to their pre-method baseline on identical routes in identical vehicles. If this video just showed you a path to cutting your monthly fuel bill by an amount that is genuinely meaningful, hit that like button and share it with one driver you know who is currently complaining about fuel prices without knowing this method exists. Subscribe now. There is a video on your screen right now that goes deeper into the Japanese maintenance philosophy that keeps fuel economy gains working at 200,000 kilometers and beyond. Click it now, and I will meet you there.